Hi, this is an example of how to compute sum square total, predicted error, the sum squared error, and the R-square value, the actual trend line, best fit trend line, using Microsoft Excel. So I'm using CDC data, just a small bit of it, with waist circumference and body mass index. Waist circumference is my X column, and body mass index is my Y column. And I chose this for a reason. So body mass index is a measure that comes from your height and your weight alone. And an argument can be made that body mass index could misclassify someone with obesity because they actually are muscular. And because body mass index can't capture that muscularity, it's not a good measure of adiposity or fatness. So some have argued for the use of waist circumference instead of body mass index. So there was a beautiful paper showing that waist circumference and body mass index were related to each other with a very high correlation. So that we're going to actually see this as we go along. I only took 50 data points from the CDC data set. It's not that many, just to test this out. So the first thing I'm going to do is I'm going to compute the average of my body mass index, which is my Y value here because it's what I'm trying to predict from waist circumference. Average is what we call a summary statistic. And we compute it by using the average command in Microsoft Excel. Average B2 colon B50 means find the average from of the column of data from B2 to B50, or that range. So we call this a summary statistic because it tells us a summary of the data that we're looking at. In some cases, you'll get the average in a class of a test. And if you know that average is 70, you have an image in your mind of what that tells you. On the other hand, if I say that the average is 70 in a classroom, and half the class failed the test and half the class got A's, that summary statistic of 70 is not a good and adequate measure summarizing the data set because we have in our minds that the data bunched up at the value of 70, and it might not be so. So this is why we compute something called the sum square total. By itself, it's difficult to look at sum square total and see some kind of meaning, but it's a measure of how varied the data is from the average. The way we compute this is we take the Y values, the actual Y values, which are my body mass index, and subtract the mean. For me, the mean value was in cell 51. So you could tell it to just look at cell 51, and that's a lazy me would do that, but you could do the hard knock me and actually put the value in. 27.111 was about the average, so we can put B2 minus 27.111, and then I'm going to square that. What the square does, it's like a magnitude. You're actually calculating the distance between the Y value and that mean. If that distance is big, then we have a problem because it tells us that the mean value or the average value is not a good summary of the data. So that's the kind of information this tells you. Now I have this for the first subject here in the CDC study, but I'm going to drag it down, and now I have my distance away from the mean for every single one of them. For example, here in this particular subject, you can see that the summary statistic of average was not a good summary of the data because this is very large in comparison with all the other ones. So I can actually see something by looking at the individual sum square. If I want the sum square total, just the square. If I do the sum square total, I would sum from C2 to C50 in this case, the entire column, and that gives me the sum square total. So I'm going to highlight that because that's one of the things that you have to know. So now, predicted. In the example you were given in WebAssign, you were given a line. So it's not the best fit line. In fact, I chose it to not be the best fit line, but it's a supposed prediction. And the prediction I have chosen is this Y equals 0.4x minus 5. So I want to see if this is a good prediction, or I want to see those predicted values and how well they compare. What that means is that my x values are going to come from column A. So if I want to give the y value given the x value of 90.7, I'm going to put 0.4 times, and I'm going to put 90.7, but 90.7 is in cell A2. So I'm going to type A2 here because I intend to scroll this down. It's minus 5, and there we go. And now scroll this down. This gives me my predicted values. I can eyeball this right here, not 29.39, 31.28. It's not bad. It's not terrible. So those are my predicted values. Just for kicks, let's compare the average here and see how it compares to the average that I already computed. You're not asked to do this, I just want to see. So I got 31 is my average here, and 27 is my average here. Does that mean that our model is overestimating? Well, let's see. The way we can tell that is by looking at the error. I actually compute the error separate from the error squared, and that's because I like to actually look with my eyes what's going on. So to compute the error, what I want to do is I want to take the predicted value, which is in this cell, and subtract it from the actual BMI, which is in that cell. So that's predicted in cell D2 minus actual in cell B2. So that gives me the error. So I have 1.89 kilograms of error. I get some bigger error there. I can actually see it as I go down. So now I can just eyeball check, as discussed in your PDF. Look here, we have a lot of error for this particular person. I can actually see it. But on the most part, it looks like it's under the 10, so it doesn't look terrible. Let's compute the error squared. So why would I compute the error squared? Well, one thing is that if I take the error and square it, then I'm not working with negative numbers. The problem with just calculating an average of the error itself is that the average of the error could be negative or positive, or like if I had an error of minus 5 and an error of plus 5, when I calculate the average, I'm going to sum those two and I'm going to get 0. So the sum square actually avoids those kind of problems. And so when we do that, and we can think of magnitude, this is coming from magnitude, to get the sum square error, I would sum from F2 to F50. And now this gives me the sum square error. Now, I would like that sum square error to be very close to 0. That would mean that my model is good. And it's not, it's 35.9. How do I know how good my model is? Well, I can calculate something called the R-square value. Recall that these are both in 51, F51 and C51. If I take 1 minus F51 divided by C51, that's where those totals were. If this F51 is very close to 0, that means my sum square error is really close to 0, then 1 minus that number is going to be very close to 1. On the other hand, if the ratio of the sum square error to the sum square total is very close to 0, again, I'm going to get something that's close to 1. R square tells you how much of the variance can be explained by your model. And you would like to theoretically have 100% of the variance explained by your model. It's never going to happen. But you'd like it at least to be above 0.90 in the case of a model. So I get 0.97521. Not bad. It's not terrible. Now the last thing is, how do we find the best fit line? To find the best fit line, it's actually a beautiful application of calculus, which I won't show you because Excel can do it for you. I'm going to highlight these two rows right here, go to Insert, go to Charts, select Scatter, the very first one, and I get this scatter plot right here. Now I'm going to go in here and right-click those data points. I'm going to get Add Trend. I'm going to use Add Trend Line. go down to the bottom. I think I did something not quite right when I selected these two. Let's see. Grabbed my averages, that's my problem. So let's not grab those averages, highlight those two again, insert, scatter plot. There we go. It's a nice line. So this is what Claude Bouchard, one of my colleagues, found, that waist circumference and BMI are related to each other. So to say that you would rather use waist circumference instead of BMI to measure adiposity or fatness, it's probably they're related to each other already. So now I can, if I check these display equation on chart, display R squared, you get up here the best fit line. That's the slope is 0.3695 and the y-intercept is minus 6.1584 and the R square is 0.829. It looks like my made up model did a little bit better in the R square. It doesn't mean it's the best fit line. So the best fit line has about a 0.83 R squared, which isn't bad in the world of anthropometrics. That's not so bad. So that closes my study of BMI and showing you what sum square total and sum square error and R square and how those computed and how to get your best fit line for using a scatter plot.